Swayam Prabha. Digital India. Educated India.
We had done a study, and you may want to look at this study, where we had calculated the life cycle greenhouse gas impacts of a coal-based power plant, and if we wanted to, instead of coal, if we wanted to import natural gas through the LNG, basically liquefied natural gas, import it from the US, look at the entire life cycle of that, and then see what happens in terms of the CO2 point of view. So if we look at this, we find that in the Indian context, most of the, as we saw, most of it is in the power plant itself, very similar to the Mann and Spat study. Here we got it as 1082 kg CO2 equivalent per megawatt hour. Mine to plant has something coming in with the mining, at mining the CH4 emissions, fugitive emissions at the mine, diesel and electricity use at the mine, and the transport. So this accounts for just 59 grams of 59 grams per kilowatt hour, or 59 kg per megawatt hour. And so this gives you a sort of breakup just from the this is cradle to the gate kind of calculation. And if we look at a similar kind of thing for the, if we wanted to use imported natural gas, we find that the power plant accounts for much lower. The total comes down from 1000 to about 585. Here the well to power plant is significant, of which it starts with the, this is where they are looking at hydraulic fracturing, and so back the production of the oil, and then processing, the transmission in the US, liquefaction, shipping, regasification. That adds much more than the mine to the well, as in the coal case where we started from coal mining to the power plant. That was very small. This is much higher, but then the actual operation is much lower, so overall it turns out to be less. We also saw, based on this, we made a distribution of the actual CO2 emissions for the coal fleet of the India, and you can see very clearly that the mean is around this. There are some plants which are more efficient, maybe they are the supercritical ones, and there are some which are operating with a much poorer emission record. And in the case of natural gas, if we had this kind of distribution, you can see that the mean would be much lower than this. So this gives you an idea of what are the kind of GHG emissions for the power sector and how we can look at it from a energy point of view. When we look at energy return on investment, there is a recent paper in Nature Energy which you may want to look at, which calculates the EROI and shows EROI for different kinds of different sources, including renewables. So we can look at the energy EROI based on primary will be whatever energy is used in the extraction and the production, but we can also look at the energy embodied and used in transmission and distribution and the final energy. So finally, if we look at this as the framework, the EROI values that we would get would be lower than that we would get only if we looked at the primary. So if we see this paper shows the EROI primary and the EROI final, and you can see over a period of time that the EROIs have been coming down, and the final EROIs we are talking of are of the order of about 30 or so, which is also a pretty high number. This is a summary of different studies, EROI estimates, and you can see here that the EROI estimates show for electricity for photovoltaics, the EROI final which we are talking of are of the order of 6 to 20, again depending on the different kinds of studies and the different kinds of estimates and assumptions which are there. In addition to the EROI, there is another EPBT, which is basically energy payback time. So, if we look at the total amount of embodied energy in, let us say, a solar PV module and see how much time does it take for us to generate that much energy. So, in the 1970s and 1980s, the energy payback periods of photovoltaics was high, which meant that it would take a large number of years for that energy to pay back. And for any new source which we consider as renewable, we can calculate this and see whether or not it is viable. So, apart from EROI, we have another index called the energy payback period. So, this is from an NREL report. You can see this NREL, if you look at this document, it shows you the kind of energy payback periods for the entire PV system, which is of the order of 3 years or less. And we can look at this data. It happens this way, that we put in all the energy in the initial period. This is when we build the PV cells, the balance of systems, and then you get the returns over the years, and then that gives you the. So, when we look at the earliest environmental impact, systematic environmental impact of photovoltaic was done by Alsema, and you can look at this paper in 2000. Start with the raw materials, go to the material processing, the manufacturing, the use, the decommissioning, and as well as some of it is recycled, and the treatment and disposal. And with this, the energy payback periods that were done for rooftop and ground mounted systems, of course this will depend on the solar insolation and the efficiencies, and based on this you can see that these payback periods are of the order of 2 to 3 years, again depending on the kind of assumptions. You can look at this paper, and this will give you, based on this we can also look at the GHG emissions, and you can see we had seen this in the initial phase where we talked about the Kaya identity, and we said that renewables are an option for us to reduce the GHG emissions. We said as compared to 1 kg of CO2 per kilowatt hour roughly for coal, when we talk of all the renewables, they are all in the range of 20-30 grams per kilowatt hour. And so these numbers are got from this life cycle analysis, and one may look at this in a little more detail. There is a recent report from the European Union which talks about the energy payback period of the recent cells, again with different kinds of efficiencies. Monocrystal silicon, if you see, it turns out to be of the order of about 2 years, and then the similar things you can look at multi-silicon, cadmium telluride, and so on. And this also gives you an idea of the total carbon footprint. We have later I will show you some numbers that we have done for an Indian context on a similar basis. When we look at the final life cycle analysis, normally you can actually use your own calculations. You can do this on with an Excel spreadsheet, or you can use MATLAB. Many of the researchers do use software for LCA, and there are a number of software, CIMA Pro, Gabi. some of them are public domain software like OpenLCA. The advantage of the software often is also that they have databases which are available for different kinds of materials, and that reduces the kind of time that you need to make the analysis. Please also remember that these databases which are there for the embodied energy will have assumptions, will be based on a certain kind of mix, will depend on the country for which it is there. So if you are doing something for India, please make sure you know how that when you use an embodied energy for some materials, find out for which country or context it is there, and is in the Indian context, is it going to be similar. You will find in all of these software, you will find that there are multiple criteria which are calculated, including the different kinds of, so there are different environmental emission factors which are there, and then the emissions are computed, both local, global. So you can see there are criteria for global warming, which is CO2, N2O, methane, CFC, and then this can be converted into a CO2 equivalent. And there are ozone depletion criteria like CFCs, HCFCs, and then there are acidifications, SOx, NOx, hydrochloric, hydrofluoric acid, eutrophication, and local photochemical smog. All of this, the toxicity, all of these parameters are there, and one gets one gets a whole set of multiple criteria. Now, depending on your application, we have to look at these criteria, see whether they are beyond the limits, compare the criteria across different options, and then then look at the implication in terms of a decision. So in many of these cases, so basically what happens is this is from the IEA's assessment, LCA assessment of different sources, and you can see what all are the adverse impacts for different kinds of sources, and then these can be quantified. One can see what kind of trade-offs one can have. Similarly, this is the LCA assessment report in terms of this is from the World Energy Council, and you can see that this has the different kinds of CO2 equivalent, tons of CO2 equivalent per gigawatt hour, and you can compare the impacts which are there for nuclear, for wind, and for photovoltaics. There are LCA has been traditionally has been very useful in seeing, for instance, when we think in terms of replacing oil, we have been thinking in terms of using biofuels, and there are a number of different sources of biofuels. One can use biofuels based on waste. One can also have dedicated plantations for biofuels, and several countries, including US and Latin America, have been having large energy plantations. And sometimes what happens in these energy plantations is one puts in a significant amount of energy in the fertilizers, in the agriculture, in the irrigation, and when you look at the overall, it may or may not be net energy positive. So there have been situations where these are subsidized, and so it looks like it's a viable option, it's renewable, but when you do the numbers, you find that this is net energy negative. So this is an example from a report which is from Science, where in the state of California, they assess that corn-based ethanol is net energy negative and is actually worse than gasoline. Gasoline is the fuel which is used for vehicles in the US, and if you look at it, this is the greenhouse gas emissions from gasoline, in terms of equivalent CO2 equivalent per megajoule of the fuel. And when we look at corn ethanol, there is a direct emission, and then there is an emission which is because of the land use change, and when you add this up, you can see that this turns out to be worse. And so of course these are interesting because as we will see when we talk about policy analysis, policymakers usually like to have a solution which is a large scale solution. So we want to have a large amount of corn ethanol, or we want to have a large amount of Jatropha, and then because it seems to be renewable, one subsidizes it, but then maybe in some cases this does not result in the impact that you expect, and you are actually putting in more energy, you are actually putting in more emissions than you would have done if you just continued with the gasoline case. So this is now a study for Germany. You can look, this is a paper by Carl Smith where a biofuel, rapeseed methyl ester for transport is calculated, and the way it is calculated, you can see the paper to get the numbers, but just to show you what it means is that the total energy that you are getting per hectare, and this we are looking at plant production including fertilizer, harvesting, transport, oil extraction, and some percentage is attributed to the rapeseed oil which is being used for our fuel, and then refining, esterification, some percentage going to be, this is what I meant when we talked about the allocation. So 96% going to this, 4% going to the other byproduct glycerine, and then final transport. So the total annual comes to about 16,200 megajoules per hectare. And if we look at per hectare, this is the amount that we will get, and this can be compared with the energy content which we are using for diesel, and we can then compare these again in terms of the emissions. So this comparison which was done in terms of primary energies, this is 16.2, 47.1 is diesel, the CO2 equivalent is 1594, in diesel it's 3752, and so overall you can see there could be in this, it looks like this is a viable option in terms of, at least primarily it passes the test of emissions and energy. So let's look at now another example which is from an Indian context. We had carried out, there was a period when the government was very keen on having large scale Jatropha plantations, and at that time we thought that it would be worthwhile, it would be interesting to see. So there was the entire map of India, you would see that there was a plan to have a large amount of Jatropha plantations, and one of the things which we felt at that time was that one needs to analyze and see whether or not this is a viable option. So this was the work done by one of our students who was interning in summer, and we compared both Jatropha and another one which is Karanj. Karanj is a seed which is used in often in South India. You can look at Jatropha or Karanj, and we start with the first phase, which is the agricultural cultivation phase. In the agricultural cultivation phase, there is some energy going into seed bed preparation, sowing, there is some fossil energy going into diesel and electricity, and there is energy going into the irrigation and fertilizers and herbicides. So that is the agricultural cultivation stage. We then take that and transport. In transport we are using some fossil and diesel. Then we have the conversion stage where you have the cracking, pressing, filtration, esterification, and then we have the fossil which is used in vehicle operation stage. and based on this we calculated using the net energy ratio, and net energy ratio, this is another energy output energy input. And in this we do not take, we are only taking for the energy input, we are not considering the energy that is put in with the biomass, we are only looking at only the fossil input. So this net energy, for it to be viable, the net energy ratio must be greater than 1. We can also calculate what is the megajoule per kilometer of vehicle driven. We can look at also the costs on a per ton and a per kilometer basis. So when we did this, if you say this, we had primary energy which was going in here, primary energy going at this point, and then we had the transportation and cracking stage, and for Jatropha and Karanj. So we did the life cycle approach, and we looked at energy output by energy input. NER greater than 1, the replacement would be viable, prima facie. Then we have to look at the economics, of course. NER less than 1, replacement not viable. Then we did the life cycle cost and annualized life cycle cost and calculated. So we can calculate it based on primary energy, on the renewable energy, and secondary. So we would like to see. And the interesting thing is, please look at this graph. These are all 2007 values. You can see that there are different kinds of combination depending on the yield and depending on the nature of the land. So if you are using fallow land which has relatively low yields, we need to put in much more of irrigation and fertilizers, and there are situations where in the case of Jatropha where this is less than 1. So the other cases where the yields are higher and we can actually get, this is without the co-product. Of course, if we are using the co-product, which is and we can actually market that, and that has a value, then of course it becomes greater than 1 for all cases. But if we are not using the co-product, which is glycerol, then you see that it depends on the kind of land. So if your yield is high, then of course we are getting an NER of 3, and in this case what happens is that this is land which is typically fertile land, and so there is an issue of food versus fuel. In the wastelands where we are looking at, if you put Jatropha, you would find that it is not viable. We are putting in much more energy than it requires, and then so this is the kind of case. Of course, this is the kind of price that we get, and the price is similar, slightly higher than the price of the fuel that we are getting ex-refinery at crude. In the case of Karanj, we find that the situation is slightly better, that it's going to be viable in all the cases. So what have we looked at? We have looked at life cycle analysis and net energy analysis, and we have looked at how to apply these, and we've looked at a couple of examples. In the next module, we will take a few more examples to illustrate the use of net energy analysis and life cycle analysis.